Hi, so now we're going to start actually solving some differential equations from scratch, namely just the one that we introduced in the last episode. So it was dy dx equals y. So last time we just guessed that y was generally going to be c e to the x, but this kind of just came out of nowhere. I mean, yeah, e to the x kind of makes sense, but I don't think we really justified fully that the general solution is just e to the x multiplied by a constant. So now, uh, we should first review implicit differentiation first, because it will be important to solving some of these more general differential equations. So implicit differentiation is essentially when you have a function of y, say y squared, but you differentiate it with respect to x. That's not really what it is, but in essence, let's say y is a function x. So what do we do with this term? Well, we can just use the chain rule, which, if you'll recall, is how we differentiate terms like sine squared x. So the chain rule says we can just treat this as like we're differentiating this with respect to just sine x. So that would be 2 sine x. But we also have to multiply by the derivative of the inside sine x with respect to x, which is cos x. Similarly, we can use the chain rule here. So we just differentiate with respect to y, but which is 2y. But we then multiply by the derivative of y, which is dy dx. So that's kind of implicit differentiation. Or another way you can write it is just dy squared is 2y dy. So normally we'd write dy squared dy is 2y. So we can write dy squared equals 2y dy, so that we can divide by x, or divide by, I say divide, but quotation marks divide, because we're taught that differentials aren't supposed to be fraction. So dx or du depending on what function of y is. Now, what's the relevance of that? Now, if we, well, I guess I'll just, okay, go back to our initial equation. So dy dx equals y. You notice we can just rearrange this to 1 over y dy dx equals 1, so that all the terms are on the left, or the y terms. You may notice this is just like a sort of implicit differentiation. So we saw before dy squared dx is 2y dy dx, which is some term in terms of y multiplied by dy dx. So I guess I'll write f of y and dy dx. So this is also some term of y, f of y, and it's dy dx. So this probably can also be written as d something, and the something is purely in terms of y over dx. Now, what function would that be? In other words, what function what function of y when differentiated with respect to y is 1 over y? Now that would be the natural log of y, right? So we can write the natural log of y over dx equals 1. And now this is just basically another way to write another form of dy over dx equals 1, except it's not y, but it's natural log of y. So the way we solved this was to integrate, right? So y is integral of 1 dx. But here it's not just y, it's natural log of y. So let me just erase this. So natural log of y equals integral of 1 dx, which is x plus c. So y is e to the x plus c. Or we can break this up as e to the x times e to the c. And this is just another constant, right? E to the c. You'll see this quote unquote trick very often in differential equations. So you can just write as another constant. Let's say k. So k e to the x. And you can see it's more or less the same form. I just changed the c into a k. Yeah, more or less the same form as our initial guess. So, so what does this mean for more general differential equations? So let's say, I guess we can just generalize this to just any function of y. So let's say y squared instead of y. Well, our first procedure would be to move whatever y term to the left, so that's 1 over y squared dy over dx. This is equal to 1. But then we ask ourselves, what function of y when differentiated with respect to y gives 1 over y squared? You might guess, oh, it's 1 over y. You can just use the power rule. Well, but if you use the power rule, you'll notice that there's a -1 sign, or just negative sign. So it's actually -1 over y. So d over d of -1 over y over dx. Again, we use the same procedure. -1 over y is integral of 1 dx. Or -1 over y equals x plus c, and y equals -1 over x plus c. So it's kind of a general procedure for just y. If the right hand side is just y and the left hand side is just dy dx. I mean, right hand side is function of y. Now, what if there is also x on the right term? So just review. If on the left hand side we have dy over dx, short review. And on the right hand side we only have function of x, and the procedure is just y is integral of f of x dx. It becomes an integral problem, purely an integral problem. If it's only a function of y, then first we move it to the left, 1 over f over y, dy over dx. And we ask ourselves, what function, when differentiated with respect to y, gives 1 over f over y, which, if you'll notice, is just an integral problem. So we ask that, and then we can just write 1 over f over y dy equals integral of 1 times dx. So this is our mystery function that when differentiate gives 1 over f over y. And this is just like what we did with the blah 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 over dx equals 1. So blah 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 equals integral 1 dx. Now, question is, what if it's we have a function of x multiplied by a function of y? Let's see an example, shall we? So let's say we have dy over dx equals x times y. How do we solve this? Well, maybe it's a good idea to still move the y term to the left side. So 1 over y dy over dx equals x. So the y terms are together, and the x term is, well, there's only one x term. Well, we can still do the same simplification. Oh, this is just the derivative of natural log of y over dx equals x. But hey, this is just a form of derivative of blah 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 over dx equals x, which is just the same as blah 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 equals integral of x dx by our first type. So in that case, this is natural log of y integral of x dx, which is half x squared plus c. Remember, or I can use the power rule. X to the power of 1, so x1 plus 1 over 1 plus 1 plus c. So y is e to the half x squared plus c. Now these kinds of differential equations consist of some function of x multiplied by some function of y are called separable. Oh, because you see you can separate them. The y's and the y's and the x's with the x's. before we end this episode, I'll just talk about a bit one other way you can think about it. So I did mention that another way we can do implicit differentiation is with dy squared, for example, equals 2y dy. Well, then y squared is just the integral of 2y or dy. And what's the point of this? Well, another way we can separate. So let's say we go back to dy over dx equals y. I mean, these are not technically fractions, but in practice here, we can separate them into their own infinitesimals. And we take integrals on both sides. So this is just natural log of y plus, say, c1 equals x plus c2. So solving this, y equals e to the x plus c2 minus c1. This is just the same as another constant, which e to the x times e to the c2 minus c1. We can call this another constant k2, let's say. So this is another way you can think of separable solution, differential equations. Now you might be thinking, well, that's fine and dandy. We can solve these specific functions, which are just a product of a function of x and a function of y. But what about function of x plus function of y, for example? How do we do that? Well, that's for the next episode.